Great, thanks very much for coming to my talk. There's been a slow and steady roll in of people through the door, which is great. But today I'm going to talk about rollouts and how to assess whether they actually worked. So we're going to be using some interesting quasi-experimental methods, and I'll explain what those are. First, a brief bit about me. I spent 15 years in academia for some bizarre reason before I moved into industry and have been very much enjoying it. My particular focus and interest is on Bayesian methods and also causal inference. And I was just chatting to someone before the talk, and it's worth kind of just laying out the groundwork that you can imagine like an axis of kind of Bayes and frequentism. That's one axis, and then another axis might be kind of stats versus causality. And in many ways, these axes are kind of orthogonal to each other. So I'm going to be talking about the causal Bayesian quadrant, but you could be any combination of those things that you want to be. Pertinent to this talk, I'm the creator and maintainer of CausalPy. I'll be going over a bit of that. And this photo is me modeling ideal data scientist behavior to my toddler. Right, so CausalPy is a Bayesian causal inference package for quasi-experiments. And quasi-experiments have a cool name, but they basically correspond to very messy situations. So we know in science that the kind of gold standard is often referred, the randomized control trial is often referred to as the gold standard if you want to make causal claims about how effective something is, no matter whether it's like a drug trial or a policy or so on. But very often in real-world situations, you can't conduct a nicely randomized control trial. You very often have messy situations, lots of confounding variables floating around, people who take part in the program or kind of take various kind of health supplements, for example, are self-selecting. And so if there is any effect of those, how do you know it's because of the supplement they're taking or because of some property of people who choose to take supplements? So quasi-experiments are basically a toolbox of approaches you can use to apply to various different situations in the world where you would like to make causal claims, but there's no randomization. And the layperson might think that this is impossible, but it is not impossible. So the package itself covers a broad range of different quasi-experimental situations, and this is growing over time. We're very grateful to receive pull requests if you would like to contribute. And today I'm going to be talking about one of these, which deals with staggered rollout situations. So staggered rollouts happen all the time. So one real-world example was the rollout of universal credit across UK job centres. So for non-UK folk, this is our kind of welfare payments system, and you could call it like politely call it aimed at getting people back into work. And this was rolled out over many job centres in the UK over 37 months. Sometimes there was a pause in the summer. Early waves of rollouts were just a couple of job centres. Later on, much larger numbers of job centres started the programme. Another example is the kind of staggered rollout of Uber and Lyft into various US cities. This took place over about a decade. And very interestingly, kind of predictable, but interesting for the richness of the problem, they targeted large areas, large cities first, and then smaller ones. So this is a nice example where the point at which your city got treated essentially wasn't randomized, it was a function of the size of the city. And so if you were trying to determine the effects of this, for example, on local employment, then you've got a non-trivial problem to solve. So why kind of tried to make the case that staggered rollouts are prevalent, just giving you two quick examples, but you can probably think of things from your own domain. But why is that the case? One reason is basically because very often it can't be otherwise. You might have operational or logistical constraints. If you're doing store refurbishments, for example, you just can't physically refurbish all your stores instantaneously across an entire nation. So there are capacity constraints. Another one might be kind of risk management. If you're kind of implementing a large change, maybe that comes with costs or potential unintended consequences, then purely for being prudent, you would want to roll out in stages. So this is very often done in software, where you roll out a small percentage of your users initially, use that to check that no unintended things happen, and then roll it out to larger and larger cohorts. So we're going to be talking about an example which I am bizarrely proud of coming up with, this business idea of a Store UK, which is a grocery store spelt in such a way that people will pay more for their groceries. Now, this gentleman here, it's not actually a photo of me. I asked for an image of a data scientist, and it happened to come up with someone who looked very much like me. So that's interesting. So this simultaneously could be a customer of Store, but this is, you're going to put yourself in the place of this data scientist who works at Store. Now, so it's a hipster grocery chain with 60 stores. And we're going to roll out a monthly loyalty program, which consists of a number of different kind of moving components, but just like a loyalty program. And we suspect that like internal Store UK meetings, we kind of expect that the revenue increase that happens in each store might happen slowly. It might build up slowly because of kind of word of mouth and adoption, basically. And we chose, Store chose to kind of roll out in 3 waves. And again, it's because there are limitations. You need to update your point of sale stuff. You need to do a small bit of staff training and do a bit of local marketing as well. So urban stores were chosen first of all for wave 1. Suburban stores were chosen wave 2, and smaller town stores were chosen for wave 3. So this is one of the key pieces here where you're noticing like a lack of randomization. So this is like statistically and causally non-ideal, but this is kind of a realistic type of situation where you've got the geography changing as each wave unfolds. We also had 5 stores that never joined the program, and that's basically purely for my own convenience to make this work, but it's also realistic. Very often in rollouts, there will be some areas, companies, stores which just don't ever partake. Importantly, when we're coming to assess this program, we've got to bear in mind that it's not free. So there's a cost involved in this program. And so what we have is basically panel data where we've got weekly revenue kind of aggregated over all of the items for every store over time, and we know the date that the program was adopted for each store. So this is like a visualization of adoption, the staggered rollout. And I'll just kind of go through this because we'll meet this plot a couple of times. The x-axis is time. The y-axis is basically store ordered by when the rollout happened. So I'm going to refer to these as cohorts 1 at the top. That's the one that received the adopted the program first. Cohort 2 are the stores that later received started the program, and then the third one later on. And then we've got at the bottom we've got our 5 stores that never took part. So we've got a whole bunch of interesting and kind of business relevant questions. Did the loyalty program increase revenue? How much? Did that exceed the costs of implementing the program? So did we get a positive ROI? And your CFO wants to know if they can sell this as a success story in order for them to get a raise. So it's very important as a hipster data scientist to conduct exploratory data analysis, and the more color you use, the better. If you don't, you get fired. So what we're showing here is revenue on the x-axis, on the y-axis, time on the x-axis, and each panel is basically the cohort. So we can see that the treatment indicated by the dashed red line happens at different points in time. We know that. And just by eyeballing it, looking at the average revenue, we can kind of get an idea that there might be an increase, but it's also not quite clear. Maybe it's just a trend because you're in your kind of growth adoption phase. So we're clearly going to have to do something quantitative in order to answer these business questions, and hopefully something kind of robust to the fact that there's lots of variance in revenue across different stores. So we go and read a book on econometrics, and we work out that when we have this kind of panel data where we've got revenue over time and we have multiple stores, that's panel data. So we're going to implement a Bayesian two-way fixed effects model, and just to briefly spend a bit of time on this equation. So T is whether you are treated, whether you are taking part in the program. It's going to be binary, yes or no. So the beta parameter is going to tell you the effect of the treatment, and that's going to be in pounds per week. But then we can't just do that. We need to take into account other things. And where two-way fixed effects is really strong is that it takes unit or store effects into account and time effects into account. And what I mean by that is if we think about store fixed effects, it's quite easy to realize that different stores are in different geographies and so have different elements of foot traffic. And they might also be different sizes. And so these are factors that vary across stores but are unchanging over time. The geography of our store does not change over time. Conversely, the time fixed effects deals with situations, factors that vary over time but affect all stores equally. So this could be things like special events, holidays. It could even be supply chain issues that affect all of your stores, for example. And so these could be considered as very, very useful ways of accounting for variance in your data, but which in some ways are nuisance variables, because what you really care about is the beta coefficient. How much lift do you get for adopting the program? So in your mind, I want you to be thinking that what this is doing is it's decomposing revenue into a number of factors, and we can visualize this. Again, we'll see this form of plot a few times. So in the main panel here, we've got revenue shown in color, and we have a visualization of our unit fixed effects on the left there, going up and down. So we can see that some stores have like a baseline high revenue, some stores have baseline low revenue. Along the bottom, we have a representation of time fixed effects, where we're noticing this is capturing the fact that there's a subtle linear trend, there's linear growth over time, but then we also have dips, for example. So this could be a time when people don't go to the store, or maybe you've run out of stock in your supply chain. So the idea is, how can we take this rich data and decompose it into a number of different factors? So that's what two-way fixed effects does. And we can do this in CausalPy. We can import CausalPy as CP or whatever you want, really. And we can use the panel regression object. And this is basically kind of like a nice, relatively concise API that we can use to do relatively clever stuff. So what we do is we pass in our data frame, and we have a formula string. So this basically says that we want to model revenue. We do not want any global intercept term. That's what the 0 does. And we have a treatment column. We also know that we have a categorical store variable and a categorical week variable. So these are going to be our fixed effects. And there are a couple of different methods we can use. Finally, we pass in a Bayesian statistical model. So there are a number of relevant ones that come packaged into CausalPy, but it's trivial to build your own custom PyMC models and inject them in. So you press go, and then you get some results. So the left panel shows unambiguously we get positive revenue growth. So we get, we're 100% sure that we get lift, and that lift is somewhere between about 2,100, 2,400 pounds per store per week. So that's pretty good. But then we look at the costs of implementing the program, and we see that the net profit is actually about minus 700 pounds per store per week. So that's not good. So we get Bayesian estimates. We get a good story in terms of there's no real ambiguity here, but it's negative in terms of the outcome. Our experiment was a failure. So that's the end. Thank you very much for coming to the talk. But that number is wrong, and I'm going to explain why that is wrong. So if we look at what this fits, this is the same equation as before. Just to remind you of what we're doing is decomposing our sales, our revenue data into these different factors. So now we've got the real store fixed effects up on the left and the real time fixed effects along the bottom. And now we're visualizing the treatment. This is our kind of staggered adoption. And you can see from the color coding that corresponds to your like 2,200 a week. And by putting these things together in the model, you can come up with a prediction on the right. And it looks quite nice. You know, it's not a perfect fit to our real data, but it's fairly good. However, we kind of notice some simplifications and some issues starting to crop up. This treatment matrix on the left is basically saying from the day that the store implements the program, you instantly get a lift, which then stays constant forever. And that runs counter to our expectation that we thought that the lift would gradually rise as adoption kind of happens. So that's a modeling simplification. So the vanilla two-way fixed effects can't account for the fact that there could be some kind of causal trajectory, so a vector of numbers of causal lifts rather than one single scalar causal lift. So without committing to anything about the shape of that trajectory, we just know in advance that it can't model it. So that motivates model 2, which is still two-way fixed effects, but now what we're doing, the right-hand side, the right part of the model looks a little bit more complicated, but all it amounts to is rather than fitting a single scalar lift, we're estimating a trajectory or vector of treatment effects. Secondly, rather than focusing on calendar time, we're now focusing on event time, so event locked to when a store adopts the policy. So two very subtle, small modeling changes, but it will increase the richness of the model. And that particular one isn't yet in CausalPy, so I used Bambi. And for anyone who's not aware, Bambi is an excellent regression-focused package built on top of PyMC. So it has all the nice Bayesian goodness. And you can see that all it took was these 2 lines. So we've got a very similar, the same formula interface, but now we've basically added in a categorical effect of event time relative to treatment. And if we do some work to do some nice plotting, we now see not just a single causal lift like you get from the two-way fixed effects, you get a trajectory. And at this point, we're starting to get kind of excited because you can see that the growth in revenue as people adopt the program has exceeded the two-way fixed effects estimate. And so there is hope, maybe, that the reality is we got positive ROI. So let's go back just to try and kind of build the insights of how this works a little bit more. Same basic plot, the main difference here is that the left panel now, rather than assuming like a step function of all of a sudden the treatment arrives on day 1 and persists, we have a trajectory. And the trajectory is the same for all of the stores in all of the cohorts, but it's obviously aligned to the program uptake. And we can now see that our predictions are kind of richer, starting to look a little bit more like our raw data. So that's nice. There is another problem with this. We haven't quite solved everything yet. And this is a bit of a subtle and a bit of a tricky one to explain. But in a sense, what's happening when you run this regression is that your decomposition into these different factors is biased by the fact that some stores who are deep into their treatment are being used as controls for other stores who have only just started their treatment. And that doesn't sound like a very useful comparison to make. You should be making a comparison to a store who hasn't had any treatment at all. That's the intuition. it's kind of subtle, and people didn't pick up on this for years. People were publishing papers using standard two-way fixed effects, basically coming up with wrong results. And these folk at the bottom kind of figured this out, that there was a problem. And now this is not universally kind of understood, but people know now that there are situations where you need to move beyond vanilla two-way fixed effects. So we need a fix to our problem. And the fix we're going to do is to change our estimation approach. Rather than decomposing all of our observations, we're going to use an imputation or a prediction framework. So now we're going to build a model, but that model is fitted only on data where there is no treatment yet. So what we're trying to do is to say, can we build a model of what the world looks like in the absence of treatment? And the reason why is because you can then do your out-of-sample prediction of what would the counterfactual world look like for a store that was actually treated. What would it look like if it had not been treated? So that's the basic logic. And then you can simply difference those two things, your estimate, your kind of counterfactual universe of the store never received the treatment versus what did happen, and the difference will correspond to the causal impact of the program that was rolled out. And we can kind of package this up into a causal estimate, so the average treatment effect on the treated stores, and we can do that as a function of event time like we did before, but we can also do it per cohort as well. So a bit of visual kind of stimulus there to kind of understand what we're doing. Step one, fitting model on untreated data only. Step two, using that model to predict the world of no treatment. Step three, subtracting reality from that counterfactual world, and the gap will give you your treatment effects. And now we're using CausalPy, but now we're using staggered difference in differences, which is a nice, concise, short object name, but it does what it says. I won't go through this line by line, but we're basically doing very similar stuff. But the operations that are happening behind the scenes correspond to the imputation approach. And now we're getting a much kind of richer picture here. So to kind of highlight what we're seeing is each cohort gets its own trajectory. Yeah, that's the key difference. There isn't just one trajectory. Each cohort has its own trajectory. And that makes sense. That makes sense as desirable because we know that each cohort has different properties. They're in different geographical regions. And that allows the predictions that the model has to be richer and closer to reality. But I should say, actually, a very kind of important aside is that when you're doing causal inference, everyone will kind of ask you how well does the model fit, because that's a question that they're used to from the statistical or machine learning world. But from the causal perspective, fitting the data as accurately as possible is not the primary metric that we should go after. It's coming up with a model of the world which is more causally accurate, hopefully, to the real world. So we do that and we get out some nice results. So we can see that we're getting trajectories and they're different for each cohort. So for the urban stores, we get a higher asymptotic revenue increase, and what is that? About £5,000 per store per week, which sounds quite nice and healthy, and it's certainly above this dashed line of 3,000, which is the cost of implementing it. The second cohort also clearly above the line, so that's probably positive ROI. The poor folk in cohort 3, though, the program did create lift. It created an increase in revenue, but below the costs. So now if we plot that, plot the ROIs, we can see that very clearly. Unambiguously positive, and this is maybe unrealistically high ROI for cohort 1. Still very impressive positive ROI for cohort 2, and sad face negative ROI for cohort 3. So at this point, you're kind of thinking as a data scientist, I wonder what the net ROI is. Is it the case that our cohort 3 stores drag the ROI of all of them down to make it kind of net neutral? And the answer is no. So the blue distribution here basically is the aggregate ROI. So somewhere between about 20 and 30%, which maps onto roughly £40,000 pounds per week across all the stores. So that's 2 million plus 2 million per year, which is pretty good. But then you start thinking, well, what if we drop the program from cohort 3 and focus on the high ROI stores? Well, in that case, you can go from your 2.1 million lift per year to 3.1 million. And so now you're starting to think that your CFO is going to pay attention to when you start going on about cohort level trajectories. And indeed he did. He listened to you and he gave you a promotion, which is fantastic. So now you have to wear a suit. There are some reasons not to use this, and for time I'll just kind of go through these quickly. But the assumption, which is valid in our particular case, is that we have an absorbing treatment. So once the stores were switched over to the program, they stayed in the program. You can do whatever you want afterwards in the future, that doesn't matter. But if you're dealing with a real-world situation where you had like a promotion, for example, and it ran for a period of time and then stopped, you would need a different method. There's also an assumption that your store revenue trajectories before the treatment are kind of in line with each other. If you've got some decreasing, some increasing, some flat, that's going to violate the assumptions of the model, and there are methods that you can use, speak to me afterwards, which can help in that situation. We also assume no anticipation. So we have a trajectory that we estimated, and the implementation of the program was assumed to have no causal effects before it was implemented. That is not always true, because, for example, if a train strike is announced, maybe you'll get like pull forward demand, people move their trips forward. So that would violate that assumption. And we also assume that rolling out a program in one store doesn't shift behavior in what's going on in other stores. So, what have we learnt? If you are doing this kind of analysis, and many people will be because staggered rollouts are very common, then vanilla two-way fixed effects are going to be a world of pain. So you would have drawn the conclusion that the program was a failure, and that would be very not good. You might stop the program incorrectly. So you want to use a different estimator which isn't subject to various biases, and you also want to kind of model causal trajectories. So we've looked at 3 models, and for kind of teaching purposes, the first 2 were problematic in terms of the estimator, but you can fix all of them. They could all use the imputation approach, for example. And none of these models are kind of correct. It depends what you think the world is like. If you do get instant kind of changes, then maybe you don't need to model their trajectory. So which model you pick depends on the mixture of like what's the stakeholder question, what's their appetite for level of detail, but also what's the complexity of the data, what does the real world look like. So in our case, our hipster data scientists who pursued complexity and accuracy wasn't just rewarded with kind of better model fits, but better causal modeling of the world. And brief plug, writing a book with Nathaniel should be out this winter. And I'd very much like to hear from you if you are using CausalPy or if you think that it could help you, and feel free to check out my website or LinkedIn. Thanks very much.